with very little doubt, AI will become, or compute in general, will become a dominant user of energy. And it is growing, and it's very difficult to predict where it will go. The error bars are really high in energy usage. So that creates a challenge because we are not really able to keep up with the unpredictable demand of AI. Yes, AI is becoming more efficient. Yes, we're building out additional capacity, but it is just very uncertain.
Okay, I want to welcome you to this week's episode of Movers and Makers podcast, brought to you by Diagon. Will Drury and I are thrilled to welcome another William, Dr. William Chueh, to today's episode. Dr. Chueh is a real trailblazer in the energy sciences and research industry or sector. He's the Associate Professor of Material Science and Engineering at Stanford Stewart School of Sustainability, Associate Professor at the Photoscience SLAC. I think Will just told me the name of it, but this is Stanford Linear Accelerator Center, the Director of Stanford Precourt Institute of Energy, and also the co-founder and Chief Science Advisor at Mitrachem. So with such a busy schedule, thank you for joining us. And we're really excited to dive in all things energy and material science. So welcome to the show, Will.
Thank you, Greg and Will, for having me.
We thought we'd just start with kind of maybe a little bit more of your personal journey. There's a very obvious theme when you look at your background. When you started to think about your career, was there a moment, a story? Was there something that catalyzed you to get in, I guess, material science, but energy is a very clear theme to your career? Was there something that catalyzed that for you early on in your career, in your studies, or your life?
As with many people, my journey also began with an outstanding teacher I had a little bit more than 20 years ago when I was a student at Caltech. At the time, I was finishing my degree in applied physics. And I thought, what could be an exciting directions to get into that is risky, that is frontier. And after much soul searching, I decided it was going to be on energy and sustainability. At the time, it wasn't a super hot topic. Solar was still very expensive. Battery was limited to niche applications. None of the things we knew today were really there. But I saw an opportunity to get into it. At the time, I was working on hydrogen production and utilization via fuel cells. And that's how I got started at the intersection of material science and energy. And that was my professor at Caltech, Susina Haile, that got me started in this topic. So it was one teacher. And this is also part of the reason why I'm a teacher today.
I got a question for you, Will. Just because I know this about your journey, you've tutored and advised several people along the way. How do you, as a professor, think about the classes of people that you bring up through your tutelage, and then the sectors that those people go on to make an impact?
Yeah, this is by far, I would say, the most rewarding and perhaps impactful part of my job, is with everything, it's all about the people. And at Stanford, we're privileged to be training some of the best minds in the world. And I would say people who train with me typically choose one of three paths. Most of them stay in sustainability and energy, typically working for startups and also large companies. That's a majority of the students. A smaller fraction get into entrepreneurship. 6 companies spun out of my group over the past 5 years. And then a smaller fraction also enter into academia, pursuing faculty positions. So we now have former trainees who are faculty members at Princeton, MIT, UC Santa Barbara, and many other places around the world. So it's really diverse. And I think that highlights the many different type of people necessary for energy and sustainability. You need a bit of everything. So we've been very proud to have being part of the journey for these students early on in their career. And the very first students I trained in the early 2010s are now really kicking butt in industry, in academia, and it's been super fun to watch.
Can you maybe to pull on the thread of this, research, how the universities basically complement private industry? You kind of are a little bit of a bridge with your work at Chem, and I'm sure others in your group. But how do you see those things complementing each other? The university, the core research with how to actually commercialize these products.
Wow, what a that's going to require several hours to answer.
Yeah.
Let me try to maybe highlight the key essence of it, the ingredients. So, academia and industry couldn't be more different. The objectives are different, the timeline is different, the source of funding is different. Um, Yet they are extraordinarily complementary. So, let me pull on a few of them. First, I think most importantly is the time horizon. At universities, our sweet spot is really sort of 10 to 20 years out. We're able to look at things that's far from mature, extremely high risk, extremely ill defined. In entrepreneurship, we often talk about things being too early, as in, oh, that sounds like a science project. But that's exactly where universities live. We love to work on science projects. And if you look back in history, many of the innovations we have today that's deployed in mass markets started in academia because of a willingness and also having the type of funding to pursue these very high risk, high reward research. So I think in many ways, I think it's the starting point for new technologies. Um, in entrepreneurship, we're very used to high level of risk taking, but in university, the level of risk taking is even higher. I would say probably 90% of the things we do don't end up where we thought it would go, and many of them end up taking much longer than we thought. But one, out of 10 ideas, one out of 20 ideas really take off. I'm in my area of expertise in batteries, and if you look at almost all major battery materials, they came out of academia. Lithium iron phosphate, lithium cobalt oxide, some of the new battery technology like solid state batteries all came out of academic groups. So I think academia has a very important role to play there. On a broader note, academia is also an outstanding world stage. Everything we do is published, everything we do is public. And this is very different than in industry and entrepreneurship. And for that reason, places like Stanford is a great stage to share with the world, also to bring the world together. This is something that we're increasingly excited about at Stanford, is that the value chain for sustainability energy is really long, involves dozens of players, even in just one area. And sometimes it's really difficult for people to connect. And one of the superpowers of universities is that we're also a very good convener. So we're able to bring people together in unique ways in order to identify collaborative opportunities, but also to align the industry to move in one direction. And that's, I think, another very important role that we play as a university. And in my capacity leading Stanford's Energy Institute, this is probably the most important thing we work on, is to think about how the many pieces of the energy transition comes together in an open, collaborative way. And the university provides the stage to do exactly that.
When you talked about risk taking, I don't associate that kind of research with risk taking, but like maybe with the university, but it obviously, like when you think about it in that context, that 90% of the ideas probably don't go anywhere or don't have the outcome maybe you kind of wish for at the beginning. But it's like a safe space to do that. That's what it's for in many ways. That's incredible.
Let me build on that because it's a different kind of risk, right? So you could say academic professors like myself are among the most risk-averse people in the world. We have a very safe job. Students don't have to worry about where their paycheck comes from. It's an extraordinary level of personal stability. But as a result of that, we're able to take on huge amount of risk in research and development, in scholarship. I think that's the key difference. It's a different kind of risk. Yeah.
I thought maybe Will and I kind of talked about this just before you joined, but AI is the topic of the day. It's kind of in the zeitgeist in a whole bunch of ways. And I wonder, we hear a lot about the energy demands of it. You hear even the big tech companies getting into nuclear and all sources of new energy. I'm just curious if you would share how you see this new wave of energy demands and how it might shape. I didn't actually associate that energy demand with batteries, but there probably is a big catalyst for energy storage as part of that. But how do you see that wave of, huge data centers with even bigger energy demands shaping stationary storage and maybe some of the broader energy mix in the U.S. anyways, I'm sure more broadly?
Greg, I think AI represents such a huge opportunity, not just on the demand side of energy, but also on solving many of the challenges we're facing. So I think there's hasn't been an opportunity as exciting as AI ever because it touches upon so many facets. So, Greg, you talked about the demand side, which I think is one of the most critical. According to a study from Lawrence Berkeley National Lab, in 2024 alone, 7% of energy in the United States, electrical energy, is used for compute. 7%.
Wow,
And
that's a big number.
today.
That's just today.
I didn't
Wow.
realize that was today.
Incredible number. And that's positioned to double or even triple in the next few years. So, with very little doubt, AI will become, or compute in general, will become a dominant user of energy. And it is growing, and it's very difficult to predict where it will go. The error bars are really high in energy usage. So that creates a challenge because we are not really able to keep up with the unpredictable demand of AI. Yes, AI is becoming more efficient. Yes, we're building out additional capacity, but it is just very uncertain. So I think from a technology perspective, it makes sense to think about how we can develop secure and reliable and affordable energy mix for AI. And there are many options, Greg, as you pointed out. We can certainly harness conventional energy, for example, through natural gas. But ultimately, we still need to think about how we can transition to a net zero economy. So really the critical technology needed is something that is energy that is available stably 24/7. And this has always been a challenge for renewables, especially wind and solar, which is not available 24/7. The sun doesn't shine all the time. The wind doesn't blow all the time either. Um, so if we think about how to take renewables and make them available continuously, then there are really sort of a few very critical technologies. Number one would be grid level battery storage, because when you combine that with wind and solar, you can get 24/7 clean electricity. The challenge there is cost, right? Solar and wind are very inexpensive by themselves. But however, if you normalize that for 24/7 clean electricity, it is considerably more expensive than conventional electricity. So that's sort of one option. Another option would be think about how we can have technologies that will give you what we call baseload electricity. So electricity that is consistently available. Um, the one that's on the top of my mind is nuclear. This has received tremendous attention over the past several years. The challenge with nuclear is, unlike wind and solar, the cost of nuclear is actually increasing with time. This is due to two reasons. One, changing regulatory landscape. And number two, that we've lost some of the expertise because most of the nuclear plants were built over 30 years ago. That remains another major opportunity. A third and a final one, as we think about baseload, is geothermal. So using the heat from the earth. Very nascent demonstration projects have been built. Huge opportunities, especially in regions like California, parts of the Pacific Rim, where geothermal energy is available abundantly. The main challenge there is exploration cost. It's very expensive to explore for geothermal currently, requiring tens or if not $100 million per exploration per site, and that is slowing things down quite a bit. So energy storage, nuclear, geothermal, those are sort of the innovations along the way that could supplement current fossil-based electricity to power data centers. So I view this as an opportunity because the demand is so high and unpredictable. Therefore, there's huge investment pouring into both R&D and deployment of 24/7 clean electricity.
I've got some questions there on, one on the exploration front, and then we can maybe address another that's related more to battery technology. So on the exploration front, when it comes to things like geothermal and even um, electricity generation for base load through nuclear, you mentioned some of the longer term obstacles and some of the just expense barriers for technologies like those. Are there any kind of current actions or areas of like study or exploration that you think could lower that risk curve over time? If there are there any technologies that you're excited about on the exploration front that could bring down that cost of searching for geothermal energy, or other things that we could be investing in that reduce the cost of nuclear as time actually goes on?
Yeah. Well, nuclear and geothermal and energy storage are in slightly different categories. Nuclear, I would say the core technology is very mature, but there it's really about the cost learning curve. So, how do we tip over the negative learning rate into positive learning rate? And it's not just technology; it is also policy, it's regulatory, it's safety. So that bucket really requires a comprehensive approach. I would say if you can get nuclear on the same learning rate as batteries and solar and wind, that would be phenomenal. And that is what's being looked at, for example, on the hypothesis of building smaller reactors and leverage manufacturing to bring costs down. It is not yet demonstrated, but our hopes are high that the cost can turn around and start decreasing with time. So that's the story with nuclear. With geothermal and batteries, unlike nuclear, the technology is not fully developed. But the challenge is the same, is how do we accelerate the learning cycle? How do we improve the fundamental technology? How do we improve the manufacturing for batteries? How do we improve the exploration for geothermal? So there, I think a partnership, say, between academia and industry is critically needed because there's still a lot of fundamental tools that we don't have. So we talked about AI. This is also where AI can help. For batteries, is really about a massive chemistry space that you have to explore, billions of permutation of what's possible to go into a battery. Geothermal is kind of the same thing. It's a massive area to explore. And AI is actually helping them both. How do we harness our large set of data, one in the periodic table, the other one in the subsurface. And using new technologies, digital twins to really accelerate that cycle can be extraordinarily helpful. But for everything I talked about, if we can get the cost down more quickly by embracing new technology, by embracing AI, that can really make a huge difference. Ultimately, our time is limited, right? Most of the climate studies show that we have, a little bit between 25 and 50 years to get things right. So there's huge pressure, and the dollar signs could not be bigger. We are estimating currently that about 10 to 15 trillion dollars per year is necessary for the energy transition over the next 25 years. Guess how much we're spending right now? We're spending just a little bit over 1 trillion. So the good news is the capital is there. But the bad news is because the risk still remains very high, the technology, many of them not yet ready, the capital isn't being unlocked. So I think that's a major challenge and an opportunity as well.
All right, that makes total sense to me. I also think it's worth pointing out that part of the solution is using some of that AI compute power today, so that we can get to energy sources, so that we can power AI compute power for tomorrow. I think is a fascinating cycle, but I agree one that's necessary. Um, there's another topic that actually I think is a good transition to into this topic. So you talked about some of the things that are going to be necessary to bridge the energy transition from where we are today into a more sustainable future. One of the topics that we hear a lot about is the transition from the previous Biden administration into the new Trump administration, and just how there have been some rollbacks of some of the programs that were really specifically geared toward renewable energy sources, things like the EV tax credits. Just to take one thing as an example, um, I think that there are certainly some bright spots in this new administration. For one, there's a big focus on AI, which is part of the reason why we're talking about this now. But I'm curious, just what are some of the things that you are thinking about when it comes to this trend towards sustainability? Do you think that this moment that we're going through is going to be a setback in the grand scheme of things, or are there some things that we have that are worth being optimistic about?
If I think about the policy of the new administration, I think I can describe it sort of in one sentence as being highly focused on American competitiveness. And I think when you apply that to energy, it actually makes a lot of sense. Energy at the end of the day must be competitive. And you can also, paint a broad stroke and say energy competitiveness is the number one priority to, say, a national competitiveness. So when energy is very expensive, the country becomes less competitive. And I think the new administration is really focused on how to make the nation competitive. Therefore, it's focused on how to make energy competitive. I think affordability and competitiveness can be a very good driver for innovation, because then the focus is on how do we get things to be less expensive. As I mentioned, that is the key challenge here. So I'm optimistic that the focus on competitiveness will allow us to allocate capital on technology and solutions that can be impactful in a short time scale. I think the balancing act is how do you maintain the long-term investments? Because solar didn't get here because it was around the corner. Solar got here because people had the foresight to invest in over a 30-year period. Same thing for batteries. Same thing for wind. It's long-term investment. So I believe that the new administration will be able to pull some of the near-term investments to make solutions more inexpensive. I am also mindful that we need to still make the long-term investment to make sure things that's coming down the pipeline 10 to 20 years out still continue to maintain momentum going forward.
What comes to mind is there, when I talk to family and friends about the energy transition, EVs and batteries, they often ask me about the holy grail, I'd say is the way the question comes to it. Maybe battery specific. Does that exist? Is there something you have hope for either in battery in general or energy production that could be a real breakthrough that would be an inflection point of it, or is that just not really exist? Or I'm sure maybe you don't know the answer, but do you have hope that there is something that can really unlock huge amounts of either production or storage, or is it just this kind of incremental and kind of things start to compound over time?
I would say when it comes to energy, it's really three words: better, faster, cheaper.
Mm-hmm.
I would love to see the need for green premium to go away. And we're already there for certain things. I think that's a major signpost. I think in terms of faster, I think this is really where AI and modern tools can make a big difference in how we accelerate the learning cycles we discussed. I think cheaper will rely on both innovation, that is bold, but it will also require incremental innovation. The 2 to 3% per year that compounds over time. By the way, that's how we got here for solar and batteries. Batteries learned at about 20% average over the past 20 years. That's how we went from $5,000 per kilowatt hour at the battery cell level to well under $100. So it's just by relatively small improvement year over year. In terms of the large breakthroughs, this is where the timescale becomes unclear. The real breakthroughs, the big ones, typically take about 10 to 20 years to fully materialize. So I think the solution is to do both. You have to make those incremental changes, but you're also looking for the big step changes. I think what the energy industry is missing is a clear, either aspirational or pragmatic roadmap, like Moore's Law, right? the semiconductor industry essentially follows Moore's law, to the letter, that you have to earn the Moore's law's learning, right? In terms of the density of compute, the hardware. In energy, there isn't sort of a curve that you have to decrease cost by 20% per year. But what if we did? If we have that target, then that helps align the industry to say, well, this is what we need to achieve. And largely, this is what has happened in the battery industry, but the coordination can be much better here. Some aspirational goal for the industry to follow in terms of getting things down to a lower price. Now, the final thing is better, right? History has shown when something is better, adoption accelerates. Lithium-ion battery is one great example. It was better than the previous generation battery, which was nickel metal hydride. And it took over nickel metal hydride in less than 10 years overall because it offered a superior experience for the customers. And this is a very hard one for energy because at the end, energy is a commodity. Just like miles driven for a mass market car or for freight. The experience isn't a whole lot different. So I also encourage people to think about, how can you create differentiation in a commodity product? So sometimes it's not in the product itself. It could be a commercial innovation. How do you decrease the cost of transaction, for example? And the innovation may come in different ways to decrease overall cost. For example, in solar, a lot of people think decreasing the cost of solar panel is key. It's not. It's actually, that's less than 20% of the total cost of solar for residential. Is actually a vast majority of cost of solar is installation. So there, better actually means, well, how do you decrease the cost of customer origination? How do you decrease the cost of install? So that better can also be broader as well. So, faster, cheaper, better. I think if you can hit 2 out of those 3 things, it will really pull technology faster toward adoption. And that's what I'm really excited by. I think it requires a great deal of coordination, partnership across multiple industries, across nations. The whole world really needs to do this together.
I have a question for you on that topic, specifically as it relates to battery. In the U.S., I actually see that there's a pretty broad diversity of battery chemistries that people are pursuing as potential better, better, faster, cheaper forms of energy. From silicon and sulfur-based batteries to LFP, lithium iron phosphate. Are there any battery chemistries that you believe have show a lot of promise for either following that transition curve or just better adoption rates overall because of abundance and availability?
Well, before I get into that, I think it's worthwhile noting it is desirable not to have a lock-in to a single technology. This is, I would say, part of the challenge with solar is because we quickly locked into silicon technology and it made it very difficult to innovate because of this massive supply chain and investment that has been made. And as a result of technology lock-in, the geopolitics also came into play, right? Because it resulted in narrowing down the supply chain, which further drives the lock-in. So one thing I'm excited by is for these new technologies, whether it's nuclear, geothermal energy storage, or whatever is needed for 24/7 clean electricity, that for each one of them, there are 2 to 3 major solution classes. So that way there's healthy competition and also diversification so we're not prone to supply chain issues, in which both of you are experts and have seen several cycles of that. So avoiding technology lock-in, I think it's very, very critical. And that's where innovation comes in. So we have to keep developing the alternative technologies. And the government policy should also encourage in diversification, which it has been so far. I think in terms of what's coming for battery technologies, recognizing there are multiple market segments. There is transportation, that's a big one. There is 24/7 clean electricity, that's yet another one. And there are niche applications, consumer electronics, defense applications. And, the first 2 will dominate in volume for sure. but the last one actually could dominate in margins. So that could be a healthy way to drive different kind of products to the market. And for that reason, I don't think there is a silver bullet for batteries because each one of them requires something different. For example, ESS is extremely cost sensitive, even more so than electric vehicles. Whereas your consumer electronic applications have relatively low lifetime requirements because devices are replaced often. And EV, you have to balance between cost and performance for the range of the car. So that already sort of gives you a hint that there will be multiple technologies spread out. Even though I'm a big fan for lithium iron phosphate, I do think there's plenty of opportunity for innovation, and I don't think that will be the sole technology available. In terms of what's coming next, I think as we think about better, faster, cheaper, I think a focus on scalability is absolutely paramount. So you can see the technology that's beginning to scale faster are those that have very resilient supply chain that has very low cost structure overall. And we're going to see more and more of that. I think using things from the ground that is abundant, like iron, that's going to make a lot of sense. But there are even things more abundant that you can utilize. For example, perhaps we can get rid of lithium. Perhaps we can embrace sulfur. These are massive opportunities for more abundant supply. Another aspect I want to highlight, Will and Greg, is the manufacturing. So a lot of people think, scaling more is all about selecting, say, a better fundamental building block like the chemistry for batteries. But it could also be fundamentally more scalable manufacturing approaches. It might surprise you to learn that battery manufacturing really hasn't changed in terms of the unit operations since its inception, and we're still using, technologies that was developed for making tape, magnetic storage tapes, from the 60s and 70s. So I think there's a ripe opportunity for looking at new manufacturing technology of the same chemistry we're using today. But can we manufacture in a way that is faster, lower emission, lower cost? I think that could be another huge opportunity as well.
We're intimately familiar with some of the cost bases. We're a big part of what we're trying to do is help folks build battery factories in short, and just to build not just a simple one, but to build a gigawatt or a couple of gigawatt hours of capacity, it's probably between $200 and $400 million just to build a baseline factory. And you see some Tesla pushing innovation with, dry coating processes versus wet, where you can kind of, cut out a big portion of the process. But there definitely is a huge amount of opportunity for innovation there, because it's I think a lot of us associate like a Duracell battery, and it seems like a very simple, straightforward process. But, in the last couple of years, I've just learned a lot. It's incredible the amount of capital investment required to build that little battery that goes into your cell phone or into an EV or a storage system. It's incredible.
So Greg and Will, I wonder if I can flip things around and ask you guys a question.
Go for it.
When it comes to manufacturing, the lock-in phenomena is also very prevalent. You tend to standardize on, one type of machine. The supply chain also tends to be very quickly locked in as well. How do we promote diversification there? So if I'm introducing a new equipment, a new process, the journey is long, certainly a decade, sometime longer. And when it comes to that faster component, I think it also applies readily to manufacturing equipment as well. How do we decrease the barrier for introducing a new process? How do we diversify the process so there's, 2 to 3 dominant manufacturing processes rather than one? What are your thoughts on that?
I think there's a lot that we can be doing to accelerate learning and development on the manufacturing technology front. For one, we tend to focus in the US, especially on the end product and development on the product design that will make an impact on the overall end use case. But just to think of some examples, there are lots of companies now that are focused on building better batteries and designing better batteries. But when it comes to the manufacturing equipment used to make those batteries, most of those companies are based outside of the US. They're in places like Korea, Japan, China, even Germany, to name a few. So I think that spending more time and focus on not just the end product design and engineering, but also on the process engineering that is the means to the end of making that end product. I think that we need to see that same intention both in academia and also in the commercial or industrial use cases as a basic starting point. When I think about the end products that we are even able to make, most of those are dictated by the tools that we choose. So, and not vice versa. So, the tools will determine the size formats that we can work with, the chemical properties of the products that can be accommodated. So, I think that having more maybe more competition there will be one of those things that helps to introduce new types of processes and new types of manufacturing equipment that will enable and unlock different types of end products. I think those are going to be a few of the things that need to happen. They're kind of a necessary component in order to make advancements on the end products that we're developing.
Thank you, Will. I'm, actually very excited to see the progress in the semiconductor industry. And that's an industry where the cycle time is much faster, not just products, but also the equipment. Once every few years, you have a completely new set of equipment coming out. And I think that's, again, driven by Moore's Law on the need to continue to bring the feature sizes down. I don't see that for the energy transition industries like batteries. I think we haven't really changed things much over the past couple of decades, not in a big way, not in the same way the semiconductor industry has embraced changes. So I've been sort of studying this myself to figure out how can we be more like the industry to have faster learning cycles, and that way we can embrace new manufacturing technologies, which ultimately lead to a cheaper product over time. So I'm excited for that possibility. And I was really glad to hear that you guys are knee deep into that as well, making that happen.
I think we have gotten to see that very up close and personal, in the battery, to see this is maybe a generalization, but at least in Korea, you see what happened was, LG, Samsung, and SK, they built the business, from back in the 70s and 80s. And the supply base is very oriented towards those traditional cell makers. And which tend to be very risk averse as well, so they tend to follow the same copy and paste system. But I think the opportunity is like with increased demand now in the US and Western Europe, there's much more like innovate. There's hundreds of battery startups, and I think those companies are demanding much either different processes, different specifications. And in some cases, we have met a handful of, Western equipment makers or at least designers and following more of a model of, designing, innovating on the system and then using contract manufacturers to build the machines, maybe in lower cost markets. And so there's early signs of it, but you do see lock in from a lot of those traditional, cell makers, and hopefully the increased demand with more cell designers and makers will, drive some of that innovation over time. And I think even you hear a lot about the Northvolt, we'll say, failure, recent kind of bankruptcy or restructuring. I think is good. It's good and bad in certain ways. Certainly we want these companies to be successful, but it's really grounding them in making scalable solutions that really work effectively. And you see that starting to shape kind of some of the future production options.
That's a really exciting point to make here, which is for anything related to sustainability, there must be a path to global impact. So that means everything has to scale. If it doesn't scale, it's not sustainability.
What would you advise if you were a young either researcher or entrepreneur? I've met a bunch of folks like this studying MBAs or looking to get into academia. What piece of advice would you have for someone that's ambitious? They want to make an impact. In some ways, it can be overwhelming because it's such a big problem. Like what do you suggest for someone that wants to have an impact in a meaningful way for their early career, or starting in their early career anyways?
I can share, I think, what's on the top of our mind at Stanford's newest school, the Door School of Sustainability. The teaching there really to our students is work backward from the solution in mind. So we are here to solve global sustainability challenges. And we need to keep that in mind. Even though the journey might be 20 to 30 years, you have to think of something that can ultimately impact sustainability at a global scale. So although we're developing one component, one ingredient, a scientific innovation here and there, but it all has to come together into the system of solutions for sustainability. So keeping that bird's eye view of the problem while you work on the very detailed problems is highly critical. Same thing for entrepreneurship as well. Most companies are working on just a small component of the overall solution. So if you keep an eye out for the big solution, I think that will keep us on the right course. I think that's very important. And for, young people getting into sustainability, sometimes it's easy to get lost in the weeds, in the little thing I have to do. But let's make sure that the little thing we do also really translate to that solution at the end. And the journey is long. So it's really important to keep this high level vision.
Thank you so much, Will. I hope
Thank
you have
you,
a great
Will.
day
Sorry for
and a
being
great
late.
week.
Greg, it was great to meet you.